Welcome to the second part of our video series where we're looking at Bayesian analysis using SPSS statistics. In this second section, we're going to be looking at prior probabilities and introducing the concept of Bayes' theorem. Now, prior and indeed posterior probabilities are fundamental to understanding how the Bayesian approach works. You may recall the slide from the previous video where we were comparing and contrasting the frequentist discipline to the Bayesian approach. And one of the last points we were making was that the frequentist approach uses only the collected data and nothing else in order to estimate a probability or parameter value, whereas the Bayesian approach uses both the collected data and some sort of estimate of the truth in the absence of any data. In other words, the frequentist tradition does not use what are known as prior probabilities, and the Bayesian approach in fact requires prior probabilities, the probability of an event occurring based on established knowledge or beliefs. Now we can illustrate the difference between these two approaches with regard to prior probabilities by looking at the age-old problem of asking ourselves, what's the probability of flipping a coin and having it land, say, heads up? If you take the frequentist tradition to its logical conclusion, the frequentist tradition says until you've collected the data, there's absolutely no way to assess the probability of getting a heads. It could be 100%, it could be 0%, or it could be anything in between. The point is you have to collect the data in order to come up with the probability. The Bayesian approach, some might argue, is a bit more intuitive. It would say, look, given that there are only two outcomes and the coin looks reasonably fair, it might be sensible at least to initially assume that the probability is about 0.5 or 50% chance of getting a heads versus a tails. Once we've collected the data, we can update this prior probability to come up with a better estimate. Now, more specifically, in Bayesian statistics, the prior probability is the probability distribution that describes the likelihood of a given value before some new evidence is taken into account. And from the frequentist standpoint, that is easily the most controversial aspect of the Bayesian tradition, the idea that you've got to come up with some sort of estimate about something before you've actually collected any data about it. So where do these estimates come from? Well, prior probabilities could be based on things like past research in the same area, or subject matter expertise, or just reasonable assumptions based on the context of the study. The prior could be the expected proportion of people likely to vote in a referendum. Likewise, it could refer to the expected mean and standard deviation of an age distribution describing, for example, when people get married. Now, in situations where we have absolutely no prior information available to us, where there has been no research done into this area for us to kind of reference, where even a subject matter expert would struggle to come up with an estimate as to a likely mean or a likely probability or a likely distributional shape, we can employ what's called a uninformative prior. And this is kind of a start point which has a minimal effect on the inference. Examples would include things like a prior probability where every outcome is equally likely. Some Bayesian analysts would argue this is actually quite similar to the frequentist tradition anyway, which says that you can know nothing until you've collected the data and everything's kind of equally likely before you collect your actual information. Now, if the prior and what's known as the posterior probabilities come from the same statistical distribution, they are called conjugate distributions, and the prior is called a conjugate prior. The posterior probability, which we haven't introduced yet, is what we get once we've combined the prior probability with our data. In other words, it's the result. And if we happen to know, there are certain situations where we're, say, doing analysis and we happen to know that we're working with data which should, be described, say, as a binomial distribution, or if it's insurance data or account data or something like that, it should be a gamma distribution, or it should be an exponential distribution, or if it's something like IQ data, it should be a normal distribution. We can specify that the prior matches this distributional shape or has the same properties to it. Now, easily, a major criticism of Bayesian approaches is that there is no single prescribed and well-defined method for choosing a prior. If you start to research this area and start to look around the web, you'll see that different analysts argue for different approaches. And furthermore, using different priors for the same problem can mean that the analysts reach different conclusions. In fact, some of them use that to their advantage. They try out different things. They kind of simulate and estimate the effect of using one prior versus another, with a view to helping it yield some insight into the phenomena that they're actually investigating. Now, with posterior probabilities, the posterior probability is the probability that results from updating the prior probability with the new data, with the new evidence that we just mentioned. The new evidence usually takes the form of collected data, and just so you're aware, from a technical standpoint, it is often referred to as the likelihood function. So the collected data is sometimes referred to as the likelihood function. So posterior probabilities come from combining the prior probability with the new evidence, the likelihood or the new data. That's what allows us to calculate a posterior probability. This all leads us nicely to Bayes' theorem, which it could be argued is the actual central contribution that Thomas Bayes himself made to the world of statistics. A theorem here isn't a theory. This is a result that can be proven mathematically from a set of axioms. So it's mathematically proven to be true, and it's expressed using something called Bayes' rule. You're going to see the following letters come up here: H for hypothesis and E for evidence. In this case, evidence refers to data, if you like, some new evidence. So what is the probability of that hypothesis being true given the evidence is expressed as the relationship between what's called the prior probability, which I already talked about, the new evidence, divided by the probability of getting that evidence to begin with. Let's just break that down so it makes a little bit more sense for most people. First of all, here's the overall Bayes' rule formula itself. Just bear in mind that the vertical line here refers to given, so that is a hypothesis. What's the probability of getting a hypothesis given that evidence, assuming that evidence is true? So the first point here is the result itself, the probability of the hypothesis being true based on the evidence is equal to the prior probability of the hypothesis being true combined with the probability of the evidence being true based on the hypothesis. What's the likelihood of the evidence being true based on the hypothesis, assuming the hypothesis is true? And divided by the prior probability of getting that evidence in the first place. So what's the prior probability of the evidence being true? What's the prior probability of getting that data? Okay, well, let's look at a worked example of applying Bayes' rule. We've got a little story here. Bernie thinks his detector has found a hoard of Saxon gold. He's got a really strong signal indicating that there's gold somewhere buried in the ground beneath his detector. And we're asking ourselves, well, what's the probability this is actually true? Well, to begin with, we need to come up with some sort of prior probability. That's our P times H part of the equation. Prior probability of finding gold might only be 1 in 10,000. Let's assume it's an archaeological site that stuff has been found there in the past, but it's pretty rare that in a given session you're actually going to find gold. So it's only 1 in 10,000. What's the probability of getting that signal, however, if it was gold? If it was gold, you would get that signal about 0.75% of the time, about 75%. So it's usually pretty reliable. And then the next thing we're asking, well, what's the probability of getting that strong signal? How often do you get a signal like that? Well, in this case, it's only about 1 in 500 times. It's fairly rare to begin with. So although the signal looks strong, the prior probability of finding gold is quite weak, and the prior probability of getting that signal is also quite weak. So we've got to combine these things together in some way in order to come up with our posterior probability. We start with our prior probability. That is 1 in 10,000. We're multiplying that by 75%, which is the probability of getting that signal if it was gold. And we divide that by the probability of getting that signal to begin with, which is about 1 in 500. That gives us a result of 0.03, so 3.75% chance, according to this calculation, that Bernie has in fact found Saxon gold. It's not very likely that he's done so. This is at the heart of the Bayesian approach, the idea that we don't just take the data, but we look at the context and the probabilities around the data itself, the probability of getting that data to begin with, and the prior probabilities, the contextual probabilities around. We combine that in order to make an estimate. And this is simply to illustrate that this is how Bayesian statistics combine prior and prior probabilities with evidence, i.e. data, in order to create a posterior probability.